I'd like to pick up where John left off, talking about what has been learned from BICEP2. I'm going to be talking about not just what we've learned about the microwave background, but what it's revealed about our theories of the origin of the universe and the origin of large-scale structure. I'll be taking a little bit different tack. I think Ed has already kind of pictured me as being bad cop here, so I'm not sure that's exactly the role that I want to take, but at the risk of being pedantic, one of the things I do want to emphasize is standard scientific methodology, scientific reasoning. It's not something that we often talk about in public, especially in meetings as this with such experienced scientists. In fact, we seldom talk about it with our students. But there are times when it's important to talk about, because if we're too lax, our thinking can go astray. And to some degree, I have a concern that that's been happening in cosmology. So let's begin with what BICEP2 has said in terms of the microwave background sky. So let's recall that in scientific methodology, in the scientific method, we don't prove theories. We don't prove that, for example, the signal is tensor. We disprove hypotheses. And then we see, after we disprove as many hypotheses as we can, what is left standing. Okay, and then we try to disprove those. And then that's the way science proceeds. But you begin by selecting the null hypothesis and evaluating it. In terms of BICEP2, the null hypothesis is pretty clear. The null hypothesis is that the signal detected by BICEP2 has nothing to do with gravitational waves, but is instead due to lensing, foreground effects, and instrumental noise. Where the foreground includes dust, synchrotron, lensing, which signals which might be mixed by filtering processes from high L's to low L's, and atmosphere, and instrumental noise. Now, at this point, we can't evaluate the null hypothesis in all these degrees of freedom because BICEP2 has still not released their systematic analysis papers. So we can only be restricted into how far we can go through this process. But of course, the focus up to this, as you know, has been on dust, which is the one place where we do have enough information in which to focus. And as John showed today, and as they showed in their papers, as they showed back in March, this is their paper representing the null hypothesis so far as dust is concerned. Now, several groups have criticized this plot for various reasons, one of which is that the curves down there include this mix of cross-polarization and cross-correlation and absolute and autocorrelation, and it's a little bit confusing because those curves represent different things. Second problem being that those curves don't include the uncertainties in those measurements. A third problem being that the error bars and the points up there don't include cosmic variance. And then finally, if we're really trying to evaluate the null hypothesis, we're really supposed to co-add lensing plus foreground plus instrumental noise, not just show one component of it. So it's a little hard to assess from this graph what the real situation is. Now, in fact, we did know quite a bit about dust prior to March 17th. Back in April 2013, nearly a year earlier. Be okay? No, okay. In 2013, nearly a year earlier, this was a plot that was presented at the S-Lab meeting in which the Planck satellite team presented their data. And what it shows is, well, the bottom curve, that black curve, corresponds to a tensor mode contribution to the B mode power spectrum, the BB power spectrum, corresponding to R of 0.1. And then the various colored plots over there represent the contribution due to dust to B mode coming from different regions of the sky with different fractions of dust in them. So depending upon the fraction of dust, the fraction of sky we're talking about, you can get a spread in what the polarization fraction or polarization contribution would be. Now, of course, the Planck satellite experiment was not measuring at the frequency of the BICEP2 experiment. This is a measurement done at 353 gigahertz. Furthermore, it's measuring over a much larger range of L modes that's relevant for detecting tensor modes. So if we, first of all, cut off the range of L's to correspond to the part that corresponds to the BICEP2 range that's relevant for detecting B modes, and then correct for the fact that we're measuring at 353 instead of near 150 gigahertz, which is where BICEP2 measures, then what happens to those curves is they move down to here. Okay, so the signal from the dust is less at 150 gigahertz, but it still towers over, it's still large, looms large compared to the tensor mode signal. So there's no reason to believe from this kind of plot that dust was an unimportant contributor to the signal. In terms of the other pre-Planck dust models that appear there, each of them should be accompanied by an error bar associated with the fact that we have an uncertainty of what the polarization fraction is. And this was nicely covered in the paper by Raphael Flauger and Colin Hill and David Spergel, in which those different bars over there represent around L equals 100 what the uncertainty is in the dust contribution, and where the middle band there corresponds to what would be the blue curve there. So the best fit dust model using pre-March 17th data would correspond to that blue curve that's shown, that blue band that's shown there with its uncertainties there. And what you can see is that by eye, and what they show statistically, is that can account for most or all of the signal. And so when we come to evaluating the null hypothesis, I think the only conclusion that one can reach given that situation is that based on the best available data at the time and now, the null hypothesis could not be rejected. Okay, if the null hypothesis could not be rejected, what are you supposed to do next? The answer is nothing. You're supposed to stop at that point. Okay, if the null hypothesis is not rejected, you don't proceed to a step 3. You do not evaluate the alternative hypothesis that the signal is due to gravitational waves in standard reasoning. And so if I show you a result that r is equal to 0.2 plus 0.07 minus 0.05, or I claim that I can rule out r equals 0 at 7 sigma, that should be a 7 sigma there, okay, that has no meaning unless I can first rule out the null hypothesis, which can't be done in this case. So I think the proper conclusion to reach this point is actually one that John stated at the end of his talk, which is at the present time we cannot say that we've detected tensor mode. The race is still on to see if there is a tensor mode or a gravitational mode contribution there. And I think that's what should be said in fairness to the theories that are competing to explain the data and the competitors that are competing to make the measurements. Now, I think also the BICEP2 experience has taught us something about the status of theory. In particular, it's taught us that something very important about the inflationary paradigm, which is that the inflationary paradigm is so flexible that no test or combination of tests can possibly disprove it. That's a strong statement. It's something that some of us have known about inflation for a number of years, but apparently is not something which is widely spoken, especially as one goes into the broader community of astrophysicists who use the inflationary model as a paradigm for explaining the origin of the universe. There's natural reasons for confusion. There's plenty of papers out there which describe models, which make predictions, which look to be testable. But I remind you that it makes no difference if individual versions of a paradigm are testable if it turns out the paradigm includes a spectrum of versions that can produce every conceivable outcome. If that's the case, then the paradigm is untestable, even if individual versions of it are. And that is the situation of inflation. In fact, as I'll point out in a bit, there are at least 3 different reasons why the paradigm is so flexible in this way. It doesn't just suffer from 1 degree of flexibility, but 3 degrees of flexibility or vagueness. Now, I don't have quite the panache to explain why, the subtleties of this reasoning, of the scientific method, but someone whom I've always admired, was a mentor of mine when I was a student at Caltech, is Richard Feynman. And actually, if you haven't looked at this before, or even if you looked at it before, you should look at it again. You should, listen to his lecture about the scientific method given in Cornell in 1964. And also at my commencement, when I graduated Caltech, he gave a famous lecture called Cargo Cult Science. I have it on my website now, and you can just find it on the web generally. I strongly recommend, if you haven't read that, everyone should read it. And if you have read it, it's a good time to read it again. But this was just a brief segment of his lecture on the scientific method in which he was talking about vague theories, which is the same as what I'm talking about, flexible theories. Hopefully the sound's going to work. Here, we'll give it a shot.
I must also point out to you that you cannot prove a vague theory wrong. If the guess that you make is poorly expressed and rather vague, and the method that you use for figuring out the consequences is rather a little vague, you're not sure, I mean, you say, I think everything's because it's all due to Muggles, and Muggles do this and that more or less, so I can sort of explain how this works, then you see that that theory is good because it can't be proved wrong. If the process of computing the consequences is indefinite, then with a little skill, any experimental result can be made to look like an expected consequence. You're probably familiar with that in other fields. For example, A hates his mother. The reason is, of course, because she didn't caress him or love him enough when he was a child. Actually, if you investigate, you find out that, as a matter of fact, he did love him very much, and everything was all right. Well, then, it's because she was overindulgent when he was a child. So by having a vague theory, it's possible to get either result.
Now, applying this to inflation, let me point out that this issue of the flexibility and vagueness of inflation, if you want to use Feynman's language, is not something which is disputed by most proponents. The leading proponents, in fact, embrace it rather than dispute it. So it's an important thing to know when you're thinking about incorporating it as a standard paradigm, because incorporating such a vague theory would be a significant departure from what I would call normal science of the last 400 years. So, for example, at a recent Harvard symposium on the cosmic microwave background, the question was asked point blank to Alan Guth, is inflation falsifiable? And his answer was, I think that's kind of a silly question. And after, you guys didn't laugh, but the audience laughed when they first heard that answer. But he actually went on to explain he was quite serious in that explanation and ended up concluding that I think inflation is too flexible of an idea for that to make sense. Well, I don't mean to pick on people, but Andre, for example, at a press conference on March 17th, stated that these results, the results that were announced by the BICEP2 group on March 17th, are a smoking gun for inflation because alternative theories do not predict such a signal, he said. This is something I've been hoping to see for 30 years. But, 4 days ago, New Scientist, he said, I don't like the way gravitational waves are being treated as a smoking gun. If we found no gravitational waves, it wouldn't mean inflation is wrong. Now, actually, there's a lot of truth to what Andre's saying there. Let's start with the second part. It's really true that it makes no difference, sorry, John, whether or not you observe tensor modes or not, because the theory is so flexible, it could survive either way. There is no test that can disprove it, including the test for gravitational waves. As for the first statement, he says the results are a smoking gun for inflation, not because inflation requires them, but rather there are alternative theories that do not. So actually there are alternative theories which are predictive, including ones that I'll talk about in a bit, which are predictive, and so the argument goes that because they make a prediction which can be falsified, inflation is left standing because it can't be falsified. But in proper scientific reasoning, what we're supposed to do is not consider models which can't be falsified. We're supposed to not let them compete with models which are subject to tests. So that's, I think, where Andre and I disagree. I think he would say inflation is better than the alternatives. But in fact, if the theory is not testable, if there's no test in principle which can disprove it, it's not supposed to be considered in the same playing field. Okay, for those of you that are not familiar with this issue of flexibility, let me just point out that, as I said, there are actually 3 important degrees of flexibility to inflation. The first is that the outcome of any particular inflationary model is highly sensitive to the initial conditions. We thought that wasn't supposed to be the case when inflation was first invented in the 1980s, but we discovered a few years later that, in fact, inflation can only even get started unless you have very special initial conditions in the first place. In fact, conditions that are so special that by some measures they're more unlikely than going straight from the Big Bang to the universe we observe without inflation. So it actually, by those measures, actually makes matters worse. But it's certainly very sensitive to them, and we don't understand those initial conditions. We have no theory of those initial conditions at present. It's also sensitive to parameters. We know that. That's why there's hundreds of models out there which have adjustable parameters and lead to different experimental results. And in recent years, there's even been examples where within a single framework model, within a single Lagrangian, there are enough parameters, enough knobs there that you can dial the parameters to go from BICEP2 results to BICEP2 plus Planck results to go to other results continuously. And then even if you fix the initial conditions and you fix the parameters by whatever means, you have the problem that inflation leads to, is eternal and eventually produces a multiverse rather than a universe. And across the multiverse, literally any physical, cosmological possibility that can occur, and will occur an infinite number of times. So even 1 degree of flexibility like this is problem enough. 3 degrees of flexibility is a nightmare. So what is the current situation in cosmology? I believe the current situation is that we must rethink the situation. And it's really quite simple. There's really one of two things that has to happen. Either we have to find a way of solving the initial conditions and multiverse problems of inflation, or we have to find an alternative. We can't stick with the current situation and stay within the domain of what I would call normal science. Now, in terms of solving the initial conditions and the multiverse problems, those are known to be hard. They've been around for nearly 3 decades, and we've known they're hard to solve. We should continue to work at them, and maybe people here have ideas on how to do that. But in the meantime, if anyone comes up later today, later this week, in some talk that you hear in the future, and talks about some inflationary model which makes predictions, I hope every one of you would raise your hand at that point and say, what did you assume about the initial conditions, and what did you assume about the multiverse problem? And if the answer is, as it often is, I've just put those 2 problems aside for now, assuming that they'll be solved later, you should take that prediction with a large grain of salt. Because not only are they assuming that those problems can be solved, but they're assuming that the solution won't affect the predictions. That even though there's this problem of initial conditions in multiverse, somehow they will play no role whatsoever in how you make, in what actually comes out as a result of the theory. And that's a strong assumption. The other approach is to look for an alternative paradigm. If you're going to look for an alternative paradigm, you're going to have to take one of the assumptions that we used in developing the inflationary model and change it. And we didn't make that many assumptions. One of the assumptions we made is that the universe began from a Big Bang in some random initial state. An interesting line of inquiry is to consider models in which the Big Bang is not a beginning, but is actually a transition from some sort of pre-existing phase, sometimes called pre-Big Bang phase or contracting phase, and expanding into and undergoing a bounce, which then takes it into an expanding phase. Now, why those particular models are interesting, I think, is, first of all, they immediately give us a sort of different approach for how to deal with the problem of the cosmic singularity, to treat it as a transition or bounce rather than as a beginning, I think is an interesting possibility. In the first place, gets around to this problem of how does time begin. Second important reason is that it immediately leads to a simple solution to the flatness and homogeneity problems. So here, just to keep the reasoning simple, I just showed the Friedmann equation in which we have matter, radiation, anisotropy, and spatial curvature. If we had small amounts of inhomogeneity, curvature fluctuations, they would also scale as 1 upon the scale factor A squared. So A here is the scale factor. This describes how much the universe is stretching or contracting. In an expanding universe, the term which decreases at the slowest rate is the spatial curvature term, and that's why we end up with the flatness problem. That's an inhomogeneity problem. And by introducing inflation, we get around that. But in the contracting universe, A is shrinking. And so as A shrinks, those same terms are actually increasing at the slowest rate. So as you contract, spatial curvature becomes less and less important rather than more and more important. And the same with inhomogeneity. In fact, the structure of the universe becomes homogeneous and flat and ultra-local, where spatial gradients no longer become important as the horizon shrinks around you. There is the issue of the anisotropy. If you want to maintain the anisotropy of the universe, there are various approaches. One, which has been explored, is the idea of introducing a scalar field with a potential which gets rid of the anisotropy in a way analogous to the way inflation gets rid of the spatial curvature. Namely, you produce an energy density which scales as a power of A, which is greater than 6, which means that the equation of state W has to be bigger. That should be P over rho. All the Greek letters got lost here. P over rho greater than 1. So it's a high pressure phase, what we call an ekpyrotic phase of ultra high pressure. And the higher the pressure, the higher the W, the slower the universe is contracting. So interestingly enough, you can homogenize and flatten the universe and isotropize the universe by ultra slow contraction or by ultra fast expansion, depending upon whether you're talking about ekpyrosis or we're talking about inflation. To get that equation of state, I'll skip. It's simple enough to just design a potential. The key difference between the potential for inflation and the one for ekpyrosis is that in inflation you want a potential which is positive and flat. In ekpyrosis you want a potential which is negative and steep. But in both cases you can produce the required equation of state. A second important reason why contracting models are interesting is they potentially evade the multiverse problem, because you're smoothing the universe during contraction rather than during expansion. So that means that although in inflation there are rare quantum fluctuations during the inflationary stage that kept parts of the universe inflating, they ended up dominating the universe and causing internal inflation in the multiverse. The analog in this case is as you're smoothing the universe, you're smoothing it during a period of contraction. So whereas normal regions will undergo a bounce and begin to expand, those rare regions which undergo rare fluctuations will continue to be contracting. But contracting regions never compete with volume with the rest of the universe. So they never come to dominate. You have no eternal smoothing process. A third reason why these are interesting, the ekpyrotic one in particular is interesting, is it gives a distinctive prediction, which is very relevant to our discussion this afternoon, is that it predicts a nearly scale invariant spectrum of density fluctuations like inflation, but a key difference being it produces no observable tensors. And the reason why it produces no observable tensors is because the smoothing is not being done when the potential energy density and Hubble constant are large and positive, but when the potential density and Hubble constant are small and negative. And the amplitude of gravitational waves depends directly on the amplitude of magnitude of the Hubble parameter, and because it's small, the tensor mode is unobservably small. So what is important about, one of the things that's important about the BICEP2 measurement and the measurements that will follow in the future is what they will say about the tensors, because they can rule out this entire range of models. This is not a prediction which can be varied. And another interesting thing about these bouncing models, of course, is you don't just have to imagine one bounce. You can actually produce models which are cyclic, which means the bounces would occur at regular intervals. And such models can be constructed in a way which is classically geodesically complete. The problem of the issue, the big key open issues in these models has to do with the bounce. Just like in inflation, there's a question of what happened at the bang that produced inflation. That's a key open issue that has to do with the initial conditions. There's an analogous puzzle or problem or open challenge which remains for the bouncing models, which is what happened at the bounce. And there's been, I'll just mention briefly, a proposal that we have been examining which takes note of the fact that as you approach the bounce, the matter sector of the theory just becomes extremely simple in the way I described before, ultra-local and dominated only by a scalar field and then to next order radiation. Massless degrees of freedom, a nearly conformal theory so far as the mass and sector is concerned. So that suggests reformulating the theory in a Weyl invariant form as we approach the bounce, where you introduce an extra Weyl scalar, which looks like it has this funny ghost-like kinetic energy there, but it turns out you can just that's just a gauge artifact. You can gauge it away. But in terms of finding solutions to the cosmological equation, it's useful to keep it there because it turns out reformulating the theory in terms of the new degrees of freedom, phi and s, you can find classical solutions which would have been geodesically complete in the original theory, which are now geodesically completable in the Weyl lifted theory. And by geodesically completed, they're completed in a very interesting way. As you approach the crunch or bang, what happens is that curvature scalars blow up, but the geodesic equations go continuously through. There are a sufficient number of conserved quantities, finite quantities, that allow you to uniquely trace the geodesics through the crunch bounce. This Weyl invariant approach can be extended beyond this toy model to all known physics. Known physics, I mean physics in the laboratory, the Higgs model, including dark matter and right-handed, should be neutrinos. And in the next days, we'll be presenting a paper, putting out a paper, which explains how you can also reformulate string theory with a local scale symmetry in target space without any fundamental lengths, in which the string tension itself emerges from a gauge fixing of a field. So it's not clear that this will have the same nice solutions as the examples that I showed before, but that's what we'll be investigating to see if we can show in this case that the classical solutions are geodesically complete. So let me just close by saying that in my view, the situation in cosmology is quite interesting. Our leading ideas at present time are flawed, or certainly missing important, huge elements in them, including the standard Big Bang inflationary model especially. And the key question for us, and the key question I think people in this audience might be able to help us answer, is did we have a bang or a bounce? And if it's a bang, what happened at the bang? How did we get in? What happened next? And if it's a bounce, what happened at the bounce? Thank you.
Thank you for that. Thank you for that presentation. We'll take a couple questions, although we'll try to get close to getting back on schedule. Raphael, go ahead.
Yeah, thanks for drawing attention to the measure problem, what you call the multiverse predictability problem, which I think is one of the central problems in cosmology. I would just point out that that problem affects all predictions, not just those of inflation, because everything literally happens infinitely many times. And it does not depend on any scale. So as long as the vacuum is stable for long enough and has positive energy, this problem will arise. What this means is that I don't think there can be a logical arrow from having inflation to saying, well, that leads to something that's just inconsistent with physics. We've observed accelerated expansion in our universe. Inflation is accelerated expansion. And so any argument that would tell us that this just leads to an inconsistency, I think confuses the fact that we don't understand how to solve a problem with whether or not something can exist in nature. Similar as one might perhaps argue that because we don't understand information in the context of black holes, you can't have any black holes in the universe.
Yeah, I guess I differ just partly. I mean, let's say I'm more optimistic than you. As you pointed out, although the universe is currently accelerating, we don't know how long that acceleration will last. So for example, in some of these cyclic versions of the models of the universe, in fact, it would not last long enough to cause the kinds of multiverse problems that you would produce. So one possibility is that we can produce theories that avoid them. And they might have the advantage that they are actually predictive, testable, and disprovable. The other line of reasoning is you're saying is we might be led inevitably to a situation where science isn't fundamentally stuck. In terms of understanding fundamental physics and in terms of understanding predictability, we're going to be having to face this measure, this multiverse, face the multiverse. A third possibility is the multiverse is simply a wrong idea. That's actually the wrong conclusion that comes out of a long-term period of accelerated expansion. So these are, I think, questions are all worth addressing because I think it's central to what we can possibly learn about fundamental physics.
So thank Paul again, please.